I'd like to thank the organizers for inviting me to speak here. So mine will be another talk on support varieties and the theme of stable module categories and related finite tensor categories. There will be some symmetric categories that come up later in my talk in characteristic 0 using Deline's classification, and I'm really hoping that someone in this room will have some information that will help in positive characteristic or other settings. So there is a little bit of symmetric tensor categories later in the talk, if you bear with me. So I just want to give the setting, and many of these things have been defined already in talks earlier today. So I'll just skim through some of this. So C will be a finite tensor category over a field. And I'm assuming that endomorphism ring of the unit object 1 is isomorphic to the field. I'll be interested in exact module categories as well. So M will be an exact module category over C. It just means that C is acting. And I'll use the asterisk star to indicate that action. I'll also assume that M has finitely many simple objects. Results later in the talk will really just be in the setting of C, the finite tensor category, but some of this will be developed in this general setting, so I wanted to start with that. I have some very simplified notation for the cohomology just to make the slides easier to write. So these have come up on earlier talks, but just H star of C is my notation for X of 2 copies of the unit object. And H star of M will be X of 2 copies of an object M of that module category M. So that's my notation. And just a couple of observations about the cohomology. First of all, the cohomology of C is braided commutative. I can't remember if that was stated earlier today. It's used. But the product was given in a very visual way in Kent's talk earlier today, right? We have extensions and we have Eleta splice of extensions. The fact that it's graded commutative uses that there's another way to define the product using tensor product of extensions. So the tensor product comes in to play in that way. So there's a graded commutative algebra. And the cohomology of M is a module over the cohomology of C via this action. Okay, and then there's the conjecture that was already brought up. Stated by Eddinghoff and Ostrich, I think about 20 years ago, that the cohomology of C is finitely generated as a K algebra. The history of that goes way back to finite groups some decades ago, and some work that Eric Friedlander did with Brian Parshall and with Andreas that was already mentioned. So these questions had been asked for some time before then. What is the setting in which the finite generation holds? What's the general setting? Co-commutative Hopf algebras, how much more general? So the cohomology of this object M being finitely generated over that cohomology, this in recent work of Chris Negrin and Julia Plavnik, who are both organizers here, they showed that as long as this conjecture holds for the category C, it will hold for the module category M. So I bundled that up in the same conjecture, but this is due to a number of different people over time. I have no memory of proving that. Sorry? I have no memory of that. You have no memory of that? Oh. I'm sure you do. Okay, well, we can. Yeah. I don't mean to sound primitive. What? I don't mean to. Okay, I had looked it up some time ago before I put it on the slides, and quite possible I misinterpreted something. We can. That's not a big deal. What? Okay. Okay. In any case, this conjecture holds in many settings that people know, and so I'm just going to assume from now on that we're working with categories for which this holds. So that's the next slide. From now on, we'll assume that C is some finite tensor category for which the cohomology is finitely generated, and there's the cohomology of an object M is also finitely generated over that. So this is the setting that I'll be working in. And under those conditions, can define varieties that have nice properties. So I'll just do a recollection Next, I'll define support varieties maybe in a slightly different way than has been done earlier today, but it all amounts to the same thing, so I'll define it via maximal ideals. The variety of M will be the maximal ideal spectrum of, there it is, of the quotient of the cohomology of C by the annihilator of H star of M. So these are maximal ideals that contain that annihilator under the Zariski topology. Could projectivize it, could look at prime ideals, and sometimes that is useful to look at it in another way. But this is how I'm going to write it today.
By the way, is there this H star of M? It's a module over H star of C. Yeah. Is there a left and right action? Or
yeah, so I guess you pick one.
And so if the category is not graded, then they are not necessarily the same. Yeah, or,
okay. Why do you have two actions? Well, there's a left action and there's a right action. Yeah, I mean, so you pick one. So I think I was picking, which was I picking? I was picking a left action. The right action is going to be connect. I have to think about it. I mean, there's certainly some, yeah, I have to dig up in my memory. There are some cases where the action is the same up to sign, but I could get something wrong if I, yeah. I'll come back to that. Yeah, that's a good question. Okay, so maybe I should just mention I'm not going to use this, but there are others who have developed similar theory, particularly in the setting of tensor triangulator categories. So Boin, Krauss, Naschel, and Solberg looked at this, and also, I believe Kent mentioned this also in his talk earlier today. So Kent Vashaw with Dan Nakano and Milan Yakimov also have developed this and in relation to the Balmer spectrum. So we heard about that earlier today. So there's this comes up, and I won't talk about that aspect, but this is related theory to what I'll talk about today. Okay, standard properties. So these are some standard properties going back to, say, finite group representations that you expect to hold in these kind of settings. And these are the easier properties to prove. So I don't want to talk about the proofs, but I did want to mention them because I'll use them later. So the complexity of an object is the same as the dimension of the variety. And the complexity is just the polynomial rate of growth of a minimal projective resolution measured by the length of the projective object Pn, or by Frobenius parallel dimension equivalently, so you can define it that way as well. The variety of a direct sum is the union of varieties. Also, if you have a short exact sequence of objects, the variety of any one of those is contained in the union of the other two. So that's very useful. And again, these are standard properties going back to when this was first developed for finite group representations, and they hold in very general settings. Okay, then we come to a property that's not so clear and doesn't always hold. But I wanted to start with it as a question. Module product property. So the question is the variety of X star M, so remember we've got a finite tensor category and a module category, and here's the object that we're getting from the action. Is that variety equal to the intersection of the two varieties?
By the way, do you want to have exact module category or any module category?
Yes, exact module category. I hope that was on the slide. I may not have said it. What? Okay. Yeah. Yeah. Okay. So this intersection property, so this turns out to be really useful when it's known. And it is known to be an equality when we're working with modules for a co-commutative Hopf algebra that goes back to work of Eric and Yulia Pavsova. Also, for some quantum groups, there's this recent work of Yulia Pavsova with Chris Negrin, and also Kent Vashaw, who's here with Dan Nakano and Yakimov again, where they looked at some types of examples, for example, some quantum Borel groups. So this module product property is known in a number of settings. When it's known, it's often useful, for example, classifying thick tensor ideals. So it's very useful. It can be very useful. Yeah.
Is it not the case that the module category tensor product property comes from, if I have the tensor product property for C over itself, do I not get it for module categories for free?
That's a great question, and yeah, I'm hoping that you can answer it after the talk.
Okay.
Yeah, I mean, it's a natural question, right? If you know the module product, you know the tensor product property for the C itself, the variety of a tensor product of two objects on C is the intersection of the variety, then do you know for all module categories? And from your paper that I'm assuming that's in there, the finite generation for module categories follows, then maybe there's a reason to expect that this is just, a little bit more work to get this module product property for. From a tensor product property, but I don't know. Okay. So maybe I should say what I do know. So this is known to be an equality in these cases, but also, of course, if X or M is projective, I should have said, you act on a projective object, you get projective when either two of those are. Also known to be an equality, this is known to be an equality in general, when you take specific objects. So any finite tensor category, module category, as long as you take X to be one of these Carlson's Eleta objects. So these are, we originally defined in the finite group representation setting by John Carlson. They're defined in exactly the same way, and that is in this general setting. You take zeta to be an element of your cohomology ring, identify it with a homomorphism, this omega, and that's the syzygy operator, or the shift functor. So identify it with a homomorphism from the shift of the unit object to itself, and take the kernel. That's it. That's L zeta. That's an object in the category C, and it turns out these objects have some very important properties. I'm not going to be talking about them for the rest of my talk, but they're going to be hiding behind the scenes everywhere. So the varieties turn out to be, the variety of L zeta is maximal ideals that contain that element zeta. And so this is the very special types of varieties. If you tensor them together, you get...
so it's a hypersurface zeta equals 0.
Yeah. And they have this tensor product property, so you can tensor them together and then get any variety you choose to realize in the larger variety of the unit object. So these are very useful objects. This is known not to be an equality, however, in some non-cocommutative Hopf algebras, some settings where the tensor product is not commutative up to isomorphism. There are some examples where it's not an equality. And these were examples that I came up with Dave Benson some time ago, and then with William Plavnik and Bergh, we've generalized to tensor category settings. So they involve group actions to mess things up. and if there's time later in the talk, I'll mention that. But what I want to spend most of the time today talking about is positive answers to that question. Okay. So the first one I want to mention, the main result is a reduction to complexity 1. Okay, so here we're working in the braided setting. So if you don't have a braided category, then I have no idea what to do other than counterexamples. But let's assume we're in the braided setting. So we have a braided category. And I'm assuming all day that it's finitely generated cohomology and so on. So the following are equivalent. The variety of this module product is the intersection of the varieties for all objects X and M. That's equivalent to saying that it's true for objects of complexity 1. So that's a reduction to complexity 1, which on the surface looks like it might be really helpful. Considering some maybe simpler objects, it is maybe not as helpful as you might think, or as I thought at first, because in fact it's hard to, if you don't understand everything already, then maybe you have a hard time doing this.
So complexity 1 roughly means that support is like a point, or? Yeah,
a point in projective version, or a line, the affine version, yeah.
So basically, if this property would be, if the point is the same, it is not, if the points are different, the product is projected.
Yes. Right. So that's really useful. Yeah. Yeah. Maybe before I get to that, detecting projectivity, just as Pavel is saying, just a quick remark is that containment in one direction is fairly quick. I mean, it's the other direction that has to be proven. So the variety of x star m is contained in the variety of x intersect the variety of m. This just follows from the definitions of the actions in the braiding. If you look at remember the variety is, what is it, the maximal ideals that contain the annihilator of the object. And so if you're annihilating, if you're annihilating x, then you'll annihilate x star m. And it works the other way around because the braiding allows you to switch order of things.
I've forgotten. Does this detect projectivity? If the variety is empty?
Oh, yeah. Let's see. So that was one of the properties was the complexity of the object is the dimension of the variety. So this will detect projectivity. Will be the trivial ones, yeah.
But do you actually need braiding, or you just need that the tensor product is commutative at the level of objects?
You just need that the tensor product is commutative at the level of objects, right? So there are cases where it's not braided, but this particular statement would still hold. Yeah, that's a good point. Yeah, like maybe some.
Well, there are lots of examples.
Like Borel, quantum Borel.
Even just samples commutative equals enough.
Yeah. Okay. Right. So okay. So even stronger statement can be made there. Yeah. Okay, so, okay, yeah, I forgot the order. I guess
what you
this
said
is
about simples?
Even being able to move the simples is fine. That's enough.
Even moving the simples is enough.
Yeah.
It's interesting.
So this slide is very busy. I just wanted to give an idea of what's behind the proof, and there are a lot of things that are swept under the rug that I'm not stating, including where the L zeta, the objects L zeta come up. But let me just try to go through a little bit of this to get the main idea of the reduction comes down to a proof by induction. So, okay, so we want to prove that this module product property for all objects x and m is equivalent to knowing it for those of complexity 1. So, of course, 1 implies 2, so we're interested in 2 implies 1. And that will be a proof by induction. We'll assume that the complexity of x and the complexity of m, they're both at least 1. So they're not projective. You've got something to do. So the induction will be on complexity of x plus complexity of m. And part 2 is the case where they add up to 2, and so that's where we get started. So how are we going to use the induction? So maybe I should first say I'm going to assume the complexity of m is at least 2. If it's the other way around and it's x that has complexity at least 2, a similar argument will hold. So this is the main idea. And there's a reduction using those objects L zeta to this special case. So I want to take M where the variety is just zero set of objects containing maximal ideals containing minimal prime P. So that's one reduction that I can make. And then next is so there are some L zetas that are coming in behind the scenes to show this. It turns out that for each maximal ideal in the variety of this object M, there's a short exact sequence with M on the right and an object W sub So fracture M is the maximal ideal, and the object is capital M, and I can't remember why we didn't worry more about the notation. Sorry about that. So W sub M maps to, this is the shift operator applied to M n times. P is a projective object. The maximal ideal M is contained in the variety of that W sub M. And here's the key point. The complexity of this W sub M is 1 less than that of M. So there's some work to do to show that such a short exact sequence exists for every maximal ideal, and it uses the L zeta. So I should have said back when I introduced those objects, they have complexity 1 less than that of the unit object, just because of the way that they're defined. So tensoring with them gives you something that you can do to get some concrete information. Okay, so once you have these short exact sequences, things will fall out. So it turns out that the variety of Wm is contained in the variety of M. Why? Remember, one of the properties said that the variety of any one of these objects in a short exact sequence is contained in the union of the other two. And the union of the shift of M is the same as, the variety is preserved under shifts. So in this category. So we get that the variety of Wm is contained in the variety of M. Also, just by the way, by this property, so this maximal ideal M is contained in, is an element of the variety. So each one of those is, every maximal ideal in the variety of this object capital M is contained in one of those. And so it's equal to the union. Okay, so putting all this together, we get the reduction. The variety of X star Wm, sorry. I'm skipping ahead. So I meant to say also, because the complexity of Wm is 1 less than that of M, we get by the induction hypothesis that this module product property holds for those. Okay, putting that together, the variety of X intersect the variety of M is equal to the variety of X intersect this big union of the Wm's, varieties of the Wm's. The induction gives us that this is the variety of the union of the variety of the X star Wm's, and then that's contained in the variety of X star M. Again, by properties of the varieties in the short exact sequence. Okay. So that's
basically,
probably, yeah.
If you have is the gist of it is the following, that if you have a variety of X star M smaller than the intersection,
Yeah.
this is what you want to prove doesn't happen. Yeah?
Right.
Yeah, so then you identify a point in the intersection which doesn't belong to the support here, and then you zoom in around this point, actually at this point, by using this Carlson objects. Yes?
Right. Okay. So there's a maybe more succinct way to explain it.
So
Okay.
where is the braiding used in this?
Sorry?
Where
The braiding was the braiding is used because the containment of
for containment.
this variety and the other one is using the braiding. It's the other way around that we're looking at here. Yeah. Yeah, thanks. Okay, so let me use that. And this was an observation that Pavel already made. Let me just go over it because this is what will come up in the example. If you think about this a bit more, there's a third equivalent condition. And this is that, let's see, so, yeah, okay, let me try to explain this. Okay, so you want to know that this is an equality for all objects of complexity 1. So you can reduce to indecomposable periodic. So that takes a little bit of thought, but we might as well be looking at indecomposable periodic objects. If this module product is projective, okay, then this will be 0 and will not be equal to the intersection if they have the same variety, right? So we want to know that as long as we have the same variety, the two have the same variety, the object is not projective, the X star M. So that's the observation. And that turns this into a more representation theoretical check. And potentially there's a more limited collection of objects, where you're looking for two indecomposable periodic objects that have the same variety, and you just want to check, you take that product that's not projective. Yeah.
Periodic is the same as complexity 1, or?
Yeah.
Yeah. Periodic, the shift is isomorphic to the original object, and that's turns out to be equivalent to complexity 1. Yeah. Okay. So this is this is the technique I'm going to use to prove this product, tensor product property for symmetric tensor categories over algebraically closed fields in characteristic 0. This is the technique. Okay. And to do that, I'll be using Deline's classification, and I've just tried to summarize exactly what I need of it on this slide, and I hope I got everything in the right place. So I'm going to assume that the field is algebraically closed, characteristic 0, and C is a finite symmetric tensor category. This is equivalent then to category of modules for this Hopf algebra, for a Hopf algebra of this form. It's an exterior algebra, semi-direct product with a group. So the group is acting, and that's giving the product structure. The group is going to be a finite group acting on a finite dimensional vector space V, and that gives an action on the exterior algebra. G will contain a subgroup of order 2, and the generator of that subgroup will act as multiplication by -1 on the vector space V. And I forgot to say it's a central subgroup. It should be a central subgroup. We use that. And one more thing, the Hopf algebra structure, the coproducts, look like this. The coproduct of V, it's a skew primitive object. It goes to V tensor 1 plus G tensor V. That G is the generator of order 2, of that central subgroup of order 2. Delta of all the group elements is H tensor H. They're group-like. So this is the structure that we need to get what we want for the module product property.
And it's equivalent to modules over this Hopf algebra on which this central element acts by parity. Yes? Like
That's right. Yeah. Okay. Yeah, I guess there's more that I didn't manage to put in the slide, but yeah, right. There are a few key properties that we need. Yeah. Okay, any other comments?
Just setting them up. This is not Hopf algebra, this is super Hopf algebra.
Super, yes, that's right.
yeah, but you can make a Hopf algebra by adding an element.
Okay. Yeah, thanks. All right. Oh,
No, this is actually a Hopf
Is it
algebra.
okay?
The coproduct is non-commutative. See?
Because,
Yeah, no, it is
because
a
it's skew
Hopf
primitive.
algebra.
Skew primitive.
there's some way of rewriting
yeah.
that.
It's a triangular Hopf algebra.
Yeah.
It's already equivalentized. It's already equivalentized.
Yes.
Yeah. Okay. Right. Thank you. Okay. So, using that, we showed that if C is a symmetric finite tensor category over an algebraically closed field of characteristic 0 again, then this tensor product property holds. And Chris is going to tell us later how to show that the module product property holds as a consequence of this. Right. Okay, great. So this is what we proved. And the idea is, well, we're going to use Deline's classification. The key case is just where this group, this finite group, is just Z2 itself, nothing more. We're in characteristic 0. The group algebra is semi-simple. It's a finite group. So it's just a bit of fluff to get from the category of modules here to the category of modules here. Right? I mean, there's work to do to relate one to the other, but it's really not the hard part. Okay, so the second step, we're going to apply that reduction to complexity 1. And what we were talking about just a little bit ago is it suffices to check that 2 indecomposable periodic modules that have the same variety have their tensor product non-projective. Right? So that's what we want to check. And that involves, the way we did it, an analogous shifted cyclic subgroups that are in this exterior algebra. So going back to work that I did with Yulia Pevsova some time ago, we were looking at some quantum groups that had these sort of analogs of shifted cyclic subgroups that the theory originally come from finite group representations. So these are just some very small, in this case, subalgebras that detect projectivity. And so we're going to want to restrict to those. And there's a bit more involved. You can induce modules and get periodic modules. But it all boils down to just checking that the restriction to copies of the Sweedler 4-dimensional Hopf algebra, checking what happens to your modules. So there's Swedler four-dimensional Hopf algebra. This is just what we just take one of these vector space elements whose square is 0 because we're in exterior algebra, and this group element, they generate a four-dimensional Hopf algebra, and that's a copy of Swedler's four-dimensional Hopf algebra. Okay, these are very small, representation theory, very well understood. So if you restrict your objects down to these little Hopf subalgebras, you can really work out what's going on. So this is, and I'm not going to do that in real time here. I just want to say this is what's going on behind the scenes.
But do you actually need
Yeah.
characteristic 0 here? Or is this odd characteristic will work?
No, we're using Deline's classification. Okay.
No, but
let
once
me
you
back
already take
up. Let me
that.
back up. Yeah. So for the statement about symmetric categories, we're using Deline's
yes.
classification. But for the statement, for all of this,
Yeah.
we need the characteristic does not divide the order of the group, at least for this
Yeah.
to get between here and here. So yeah, the statement is really more general. Yeah.
But even if it divides the order, maybe you can combine it with the known theory for groups, and it still will be true.
Okay, that's a good idea. We have not tried that. Yeah. Thank you.
So is this
Yeah.
not like it seems like a rank variety type of a thing.
Yeah, and I probably should have mentioned that. Yeah, so we can, so we did.
Like happens to look like a rank variety type of thing, or
So we didn't develop that. So the work that I did with Yael some time ago, we defined a rank variety for some quantum elementary abelian subgroup. So it's not exactly this, but it's fairly similar to this. And in this paper with, this recent paper, we didn't try to develop the rank variety,
it's like similar.
but we could have. It would surely be similar, and we could probably develop that. We didn't. I should say that this reduction to complexity 1 result, that's been, we've had that for some time, and we didn't publish. We didn't try to publish or write up that. Just put it on the archive last summer. We didn't try to put it on the archive because we were looking for an example, right? Okay, so we couldn't find a new example. So the only examples we were able to compute for a long time were examples where it was already known, this tensor product property. And at some point we realized that we could get something new if we were looking at these symmetric tensor categories, that just by fiddling a little bit with what had already been done in related settings. So.
But I have a question.
Yeah.
So I was under the impression that something was known about the finite supergroup scheme, that there was some support theory for.
Unipotent ones. There's general theory for unipotent ones.
Only for
And
unipotent?
positive
I think
characteristics.
John and I wrote something about characteristic 0 finite supergroups in one of our papers some while ago. It looks like these smash products.
Okay.
Exterior algebra.
Because these are just all finite supergroup schemes. Characteristic 0.
Yeah.
Basically, the same.
So this fits into that theory, basically.
So I think
And it sort of boils down to just supports over exterior algebra, and that's the literature going back even further.
Okay.
Okay, so it's quite possible that this is not really that new, but we were ready to get this out the door. We were getting really tired. So I would be really happy to hear more about, what's already known that we somehow didn't find in the literature, or maybe related, categories or settings where these techniques would work. It was really frustrating that we had this reduction to complexity 1, and somehow that wasn't helping as much as we had hoped it would. So, but anyway, this is a statement about symmetric tensor categories, so that justifies my talk in this this conference. I wanted to say something about that. Okay, any other comments about this? Okay. So in the rest of my talk, I wanted to back up just a little bit and summarize again. So what are some of the open questions? And then I'll go on and look at the negative answers that I mentioned some time ago. Okay, so again, is the cohomology of a finite tensor category finitely generated? This question come up in earlier talks, and it would be really nice to have more information. Because a positive answer does give some good support varieties. And the question about the module product property is the variety of x star m equal to the intersection of the two varieties. And again, that's known in some settings, and it's known not to be true in others, and that's what I want to talk about next. But where does the dividing line sit? So the question is about braided. The examples I'm going to show you in just a little bit of negative answers to that question are not braided. And so the question was, well, what about braided categories? Do we always get this module product property? That's where the question's coming down now. Okay. So here are the negative answers. So let me I'll run through the theorem statement. The way it's stated is maybe not as helpful as it was intended to be. So we're going to let C be a perfect field, and I'll explain why maybe on the next slide. K is a perfect field. You could take it to be algebraically closed if you like. C is a non-semi-simple finite tensor category with finitely generated cohomology. Then the statement is that C embeds as a finite tensor category into a finite tensor category also having finitely generated cohomology, but not the support variety tensor product property. So that's the statement. It's not, doesn't really give you a whole lot of information. So that's on the next slide, but I did want to mention this, that we have loads and loads of examples. So we could start with any non-semi-simple finite tensor category, and we can just embed it in loads and loads of categories that we can even start with a finite tensor category that doesn't have the tensor product property, or maybe it does. Either way, we can embed it into loads and loads of categories that don't. So I can explain what, yeah.
Isn't it enough just to have one example, and then you can answer C with that example?
Oh, sure, yeah. Yeah. Yeah, I mean, it's enough to have one example if you want a counterexample.
Yeah.
Yeah. But I think
I mean, to this theorem.
Oh, yeah, okay. The way this theorem is stated, like I said, is not very, not very informative. So I'll get to maybe a more informative statement next. Yeah. Okay, so there's a bit more on this slide. So here's how we construct our counterexamples. And before I get into the weeds, I just want to put out there the question, are there other types of counterexamples? I mean, these counterexamplers are constructed in a particular way with a finite group action, and I'll go through that. But the question is, are there other types of counterexamples? And I know that maybe I meant to mention this, came up in Kent Vashaw's talk earlier. So in his work with Nakano and Yakimov, they were looking at a tensor product property, but they were looking at a little bit different statement of tensor product property than the one that I'm looking at. They were looking in the non-commutative tensor product setting, but they weren't looking at individual objects. They were looking at a whole set of objects, and so that came up. So there are ways, even if the tensor product property doesn't hold or the module product property doesn't hold, maybe there's some modification that does hold, and it for their theory, these are no longer counterexamples, right? For their theory, they will satisfy the tensor product sort of more general non-commutative tensor product property that Kent and the others have, right? That's correct. Yes. Okay. Yes.
You're talking about homological.
Right. Okay, so maybe I should back up a little bit further. So this is cohomological support. They were talking about both cohomological support and the Balmer and the central. So there's a little, they're a little bit different setting. You're right. Yeah.
But the question is, do you have an example where you have inclusion in one direction but not in the other direction? Because in this example, you will not have an inclusion in either direction. Because it's twisted. It's true, but after a twist.
Mm-hmm. Yeah.
But do you have examples when there is a proper inclusion in one direction, but not in the other?
Do you mean
That like well, you have variety of x cross m, and variety of x intersects with variety of m. So do you have an example when one set is strictly smaller than the other?
So I believe so, but let me go through this, and then I'll think about it a little bit more. I mean, there are loads of ways you can. I mean, you
Because
can
this
pick
way,
your object
you
this
cannot
way or
do
that
it
way.
this way. You will not be able to do it this way, I think, with the group elements.
Okay, then maybe we need to look at that. Yeah.
I think you can.
Yeah.
I mean, what they construct is two non-projective modules and kind of tensor
I think
product.
the original example with you and Dave was you take a module such that some tensor power is projective. Then that is empty and it sits inside the intersection of the variety of the original
Yeah, I
module.
think it needs the counterintuitive equation does hold, and it's the stupid one, the one that you expect to hold is the one that
No, but I mean holds in one direction for all
All
objects.
of this.
Yes.
Oh, for all.
Yeah.
Oh, okay. Okay. Maybe that's a different question. Yeah. Okay. Let me go through this. So here's how the group action does something for us. So we're going to start with a finite tensor category C and a finite group acting on it by autoequivalences. And the category that we're interested in is the cross-product category C with G. And the objects are going to be indexed by the group elements, direct sums over the group, take objects from C paired with elements of the group, this finite group. The morphisms are component-wise. The tensor product is mixing things up by applying the group action, right? So this tensor product, the notation is supposed to remind us about semi-direct products of groups, and that's exactly how the tensor product works. So M paired with G tensored with N paired with H is M tensored. G has to act on N. So in order to move a group element past an object, it has to act on that object. So this is highly, for most choices of C in group actions, this is highly non-commutative tensor product, right? It's not going to be braided for most choices. The unit object, there is a unit object, however, it's the unit object of the original category paired with the identity for the group. So as a abelian category, this is really just the Deligne product of C with G-graded vector spaces, but the tensor product is mixing things up, and so it's a little bit different. But that maybe helps to visualize the cohomology of this category is the same. Let's see, where are we? Yeah. The cohomology of this category, this cross-product category, is really the same as the original, for the original category, right? This is a semi-simple piece that we've got over here. And so the support varieties are really the same, in quotes, as for the original category. Meaning, so what would be the support variety of this would be you would take the forgetful functor to the original category and then take that. Is there, okay. I mean, if you have an observation that's helpful. Okay, all right. Okay, so then this tensor product, the definition of the tensor product in the category gives you automatically this sort of funny property on varieties. The variety of mg tensored with nh, sorry, let me back up. Assume that the category C has the support variety tensor product property. So the variety of a tensor product is the intersection of the two varieties. Then using this definition in the cross product category, we get some funny property, and that is the variety of the tensor product of these two. That's going to be the variety of M tensored with G acting on N, but that's the intersection of those two, right? So the variety, and I probably should have written out a little bit more, you can see that if G moves in very far, right, if G of N is very much different from N, maybe it has a different variety than N, then you're not going to get the tensor product property on this cross product category. Right, okay. So here's the statement that maybe has a little more information than the one in the previous slide. K is a perfect field, and I should say we're using this because we're referring to work of Chris and Julia in relation to the Deligne product and field extensions. And so we're just grabbing their results out of a box, and that's the only reason why we're taking a perfect field. We have the Deligne product here, so we need to make some assumptions. Assume C is non-semi-simple. Let's just take the group of order 2. with non-identity element interchanging two factors in the Stirling product of C with itself. Okay, so just switching them around. There are loads and loads of other constructions you can do, but this is one that works. Then this cross-product category, where you're taking this 2 copies of C and you're taking the sort of semi-direct product with Z2, switching the factors, does not have the support variety tensor product property. Why? Because you can choose an object that's projective in one copy and non-projective in the other copy, right? And then pair it with the non-identity group element, take a tensor product of that object with itself, it's going to switch the order, and you're going to end up with something that's projective. But the intersection of the varieties would not be 0. So, okay, so that's the construction. And like I said, there are loads of other choices of group actions and so on that you can do to get some counterexamples to the support variety tensor product property. And I would love to see more different types of examples. Okay. Yes.
Have you ever considered the variety of the orbit of the objects, and like what kind of properties does it have?
Yeah. So sorry, we have not, but certainly if you take orbits, you're going to mess up this this part of the argument. I believe that someone has looked at the Drenfeld double of one of these, and then it becomes braided, and then so what you said reminded me of the Drenfeld double. It becomes braided, and then I think you're back. You don't have a counterexample anymore to the tensor product property, but I haven't looked at any of the details. I don't know if that answers the question. Yeah. Okay. So this is all that I had to say, and I just want to say again, back to the setting of symmetric tensor categories. If anyone has any idea what to do, for example, for positive characteristic, is there something that we can do? If you understand, say, complexity 1 objects well enough to try to investigate the tensor product property for those, like the Verlinde p to the n categories, which I am really interested in, but have never really taken the time to study them enough to try to answer any of these questions. So, but anyway, if anyone has more information or more ideas, I'd really appreciate hearing. Thank you.